Good day, everybody. Today, we'll be talking about intermolecular forces. As the name suggests, intermolecular forces are the forces in between molecules. Intermolecular forces, or IMFs, is responsible for the very existence of different physical states like solids, liquids, and gases. A gas can be pictured as a substance whose component particles are far apart, are in rapid random motion, and exert relatively small forces on each other. The kinetic molecular model was constructed to account for the ideal behavior that most gases approach at high temperature and low pressures. Solids are obviously very different from gases. A gas has low density and high compressibility and completely fills its container. Solids have much greater densities and are compressible only to a very slight extent and are rigid. A solid maintains its shape irrespective of its container. These properties indicate that components of a solid are close together and exert large attractive forces, for example, intermolecular forces, on each other. The properties of liquids lie somewhere between those of solids and gases, but not midway in between, as we can see from some of the properties of the three different states of water. The relative similarity of liquid and solid states can be seen in the densities of three states of water. The densities for liquid and solid water are quite close. As we can see, the densities for both the solid and the liquid states are relatively high compared to that of gas states. The liquid shape is indefinite as it takes the shape of the portion of the container it occupies. However, because the molecules in the liquid phase, it's still close enough to each other, so it does have definite volume, similar to what you see in the solid. The conclusion is clear. The liquid and solid states show many similarities and are strikingly different from the gaseous state, as you can see in the pictures. Let's quickly summarize what we just talked about. The most important manifestation of intermolecular forces is the very existence of the liquids and the solids. Without the intermolecular forces, solids and the liquids would not even exist, and all matter would be gaseous phase. In liquids, we can observe several other manifestations of intermolecular forces. For example, surface tension and viscosity. We will go into the details in a little bit. Let's look at some examples, try to solidify what we just learned. A force that occurs between molecules is called that's what between means. It's intermolecular forces. And so-called intramolecular force is the force inside the molecule, and these usually refers to chemical bonds. Intramolecular forces are chemical bonds. For example, covalent bond, ionic bond, or metallic bond. Let's look at another practice. Which pure compound has the highest total intermolecular forces per molecule at 25 degrees C. When we look at this whole list of compounds, they exist in different physical states. Carbon dioxide at 25 degrees C exists as a gas phase. Water is a liquid at 25 degrees C. Rubbing alcohol is a liquid as well. Table sugar is the only solid that you see in the list. Gasoline is in liquid phase as well. As we just learned in the previous slide, the solid phase has the strongest intermolecular force, and the gaseous phase has the weakest intermolecular force, while the liquid phase will exhibit moderate strength of intermolecular force. So for this reason, for this question, the only solid, table sugar, will exhibit the highest total intermolecular force. Let's look at another example. Which property describes a molecular liquid? A. The molecules are close together. As we can see in the pictures over here, the molecules in the liquid phase are still close together. B. The density is higher than its gas. In gas phase, the molecules are far apart, resulting in a much lower density for the gas. C. It's not compressed easily. That's correct. The liquid molecules are close together, so the compressibility is still relatively small. D. It assumes the shape of its container. A liquid phase does assume the shape of the container that it occupies. So all of these statements are correct. A substance has a definite shape and definite volume. What is the state of the substance? The correct answer would be A. A solid has a definite shape and a definite volume. A liquid would have indefinite shape but definite volume. A gas would have indefinite shape and indefinite volume. It will take the volume of the corresponding container, which can change. Hopefully, these examples will help you understand more about the properties we have learned about the three different physical states: solid, liquid, and the gas states. Now, let's talk about the other manifestation of intermolecular forces, that is, the surface tension, viscosity, etc. We're going to go over surface tension first. You might have noticed we can actually float a paper clip on the water surface if you carefully place the paper clip over the top of water. The reason is because of the intermolecular force. However, you cannot float a paper clip on gasoline. This is because the intermolecular force among the molecules composing gasoline are weaker than the intermolecular forces among water molecules. So it's not the intermolecular force amongst the gasoline molecules are not strong enough to support the paper clip. We know this floating of paperclip over the surface of water is not a result of the density, because as a matter of fact, the density for the paperclip is much bigger than that of water. What happens is the surface molecules in the liquid water, as you can see, they are undergoing attractions with less neighbors. And for the molecules inside the liquid, they interact with more neighbors. So what happens as a result of this interaction is that the water would like to shrink to make the volume as small as possible. And this phenomenon is called the surface tension. In the case of a paperclip, it seems like the water forms a network of intermolecular force which supports the paperclip, making it float on the surface of water. Another phenomenon that can be explained by the intermolecular force, and is also an example of surface tension, is that water drops actually exist, most likely spherical. Water drops are spherical is because of the surface tension caused by the attractive forces between the water molecules. As a matter of fact, on the space shuttle, the complete absence of gravity will result in the floating spheres of water, as you can see over here. The spherical shape has the smallest surface area for the same volume. This is a result of the intermolecular force, which causes the liquid to shrink into the shape of a sphere. So we just learned two examples of surface tension. The first one, paperclip floating on the surface of liquid water. Second example, water taking the shape of a sphere. Let's now talk about viscosity. Viscosity is the resistance of a liquid to flow. Liquids that are viscous flow more slowly than liquids that are not viscous. For example, motor oil is more viscous than gasoline, and maple syrup is more viscous than water. The viscosity is greater in substance with stronger intermolecular forces, because the liquid molecules will be attracting to the neighboring liquid molecules with the stronger force, resulting in the stickiness in the liquid. So for this reason, if intermolecular forces are stronger, the viscosity of the liquid will be greater. Another aspect of viscosity can be generated by the length of the molecules. The longer the molecules, the better chance for the molecules to entangle up, then the bigger the viscosity. For example, in the motor oil, the molecules tend to entangle with each other, resulting in the viscous liquids. Let's look at a few practice questions. Why doesn't a paper clip sink when the clip is placed gently on water? This is a phenomenon that is called surface tension. It's not because of the density. This is because of the intermolecular force in between water molecules that attract each other, so it keeps the paper clip from sinking. So the correct answer would be E. Let's look at another example. Which of the following has the highest viscosity? A. Oxygen gas is in gas phase. There is no meaning to talk about viscosity for gaseous substances. Second, pancake syrup, as we know, it's very sticky. It has very high viscosity. Running water does have some viscosity, but it's not as viscous as the pancake syrup. Similar conclusion can be drawn for liquid helium and the rubbing alcohol. So the correct answer is B. Pancake syrup is the most viscous. Which of the following is or are true for viscosity? A. Substances with stronger intermolecular forces are less viscous than those with more. That's apparently a wrong answer. Molecules with greater length have greater viscosity. That is correct because the longer molecules will have better chance to get tangled up, causing greater viscosity. C. Substances with stronger intermolecular forces are more viscous than those with less. That is correct, because molecules will be more attracted to the neighbors, and the property that is shown will be higher viscosity generated by the stronger intermolecular force. So both B and C are correct. We'll pick actually E as the correct answer. Surface tension and viscosity are two of the very important macroscopic properties for liquids. Vapor pressure is another important property for liquids. Vapor pressure is defined as the pressure that is generated by the gas molecules that have escaped from the bulk liquid. When temperature is increased, the vapor pressure will increase. When the intermolecular forces of the liquid molecules decrease, the liquid molecules are more likely to escape the liquid bulk and become vapor. So, decrease in strength of intermolecular forces will increase the vapor pressure. Do remember, the vapor pressure is independent of the surface area, because an increase in the surface area at equilibrium will equally affect the rate of evaporation and the rate of condensation. Do remember, if you see a sealed closed container with some liquid inside, at equilibrium, both the liquid molecules are being converted to the vapor, and at the same time, the vapor molecules are being condensed back to the liquid phase. But at equilibrium, the rate of the vaporization and the rate of condensation are exactly the same. When the surface area of the liquid increases, it increases the speed for condensation and that of the evaporation at the same time. So the vapor pressure is not going to change because of the change of surface area. The rate of vaporization will increase with the increase in surface area, as evidenced by the fact that if you have a puddle of water, if you spread it out, it dries out more quickly. It's also true when you increase the temperature, the rate of vaporization also increases. When the molecules have smaller intermolecular force, the molecules are more likely to escape the bulk, resulting in greater rate of vaporization as well. And for the liquids that evaporates more easily, we call them volatile liquids. While those do not vaporize easily, we call them non-volatile liquids. As we just explained, in a sealed container, as you see over here, initially this container is capped, and the liquid molecules will escape the bulk and become gas molecules. When you have more and more gas molecules being formed, do remember at the same time the gas molecules has changed to go back to the liquid phase. At equilibrium, you will see no net change of the volume of the liquid and gas, because at this equilibrium, the rate of evaporation and the rate of condensation will be exactly the same. At this point of time, we say the process is at equilibrium. Since both processes are still going on, the condensation and evaporation are still going on, we call this equilibrium a dynamic equilibrium. Evaporation and condensation are two of the 6 physical changes. For example, melting is the process from solid to liquid. Freezing is the liquid going back to solid. Sublimation is the process from the solid to gas directly without going through the liquid stage. interposition is gas to solid. If we can summarize this in the triangle, you can write the solid at the bottom and liquid in the middle, and then gas phase at the top. So in this case, if you look at energy, energy will increase from top to bottom. When you convert solid to liquid, this is called melting. When you go from liquid back to solid, this is called freezing. If it's liquid being converted to gas, this is called evaporation. Gas back to liquid, this is called a condensation. If it's the gas going back to solid, this is called deposition. And solid being converted to gas, this is called a sublimation. You must be 100% familiar with all these 6 different processes. Another aspect is, are these processes endothermic or are they exothermic? Endothermic means heat is needed for this process to happen. Heat will be absorbed. Exothermic means in that process, heat will be released. So when you look at this process, melting, when you see the arrow going up, for melting, that means it's endothermic. Heat is needed for this process to happen. Liquid going to gas, the arrow is going up, the process is endothermic. When the arrow is going down, for example, gas going back to solid or deposition, this is an exothermic reaction. In this process, heat is being released. The opposite is also true. When solid is being converted to gas in the sublimation, this is endothermic because heat is being added for this sublimation to happen. So let's work on a few exercise problems. What is the relationship between external pressure and the boiling point of the compound? As we have observed, the higher the external pressure, the higher the boiling point. The lower the external pressure, the lower the boiling point. So anytime if you see choices like E, 2 if above, or 3 if above, we have to complete reading all the choices. Choice A, the boiling point increases with higher pressure. This is a correct statement. B, the boiling point increases with lower pressure. That's not correct. C, the boiling point decreases with higher pressure. That's not correct either. E, the boiling point decreases with the lower pressure. That's also correct. So for this reason, both A and D are correct. So we're going to pick E, 2 of above, as the correct answer. Which of the following processes are exothermic? Still remember, if you do the triangle with the solid at the bottom and the liquid in the middle and the gas at the top, you do know when you're going up, arrow going up, that's called endothermic. When arrow going down, that's called exothermic. Exothermic, exothermic, exothermic. So gas to liquid, condensation, that's exothermic. Okay. What about freezing? This is freezing. This is condensation. So both B and C are correct. So we pick E as the correct answer. Which statement is most likely true concerning the ice and water mixture kept at 0 degrees C? If you recall, when the sample is kept at the boiling point, okay, you have both processes going on at the same time. So evaporation rate and the rate of condensation will be exactly the same at dynamic equilibrium. And that's not unique. When you have a solid phase and a liquid phase kept at the melting point, as you are being asked over here. So the mixture is kept at 0 degrees C. What happens is this process is at dynamic equilibrium, or the rates of freezing and melting are equal. So E is the correct answer. This is exactly the concept of dynamic equilibrium. So basically this tells you the rate for a forward direction and the rate for reverse process are exactly the same. Which of the following is the most volatile? Volatile means lower boiling point. So gold at very high melting point and even higher boiling point. Vegetable oil, water, mold oil, fingernail polish remover. If you have used a fingernail polish remover, you will notice shortly after you apply the fingernail polish remover, then it evaporates. That means this is the most volatile. All right, now let's go over the details about the different types of intermolecular forces. We have 4 different types of intermolecular forces. We're going to go over them one by one. The first 3 are dispersion force, dipole-dipole, and the hydrogen bonding. The strength of the intermolecular forces between molecules or atoms, we call them intermolecular force. The strong intermolecular force tends to result in liquids and solids. We have already learned this in the first few slides. The weak intermolecular forces tend to result in gases. So here we focus on 3 fundamental types of intermolecular forces in the order of increasing strengths. They are dispersion forces, dipole-dipole force, and hydrogen bond. So what is dispersion forces? Dispersion force is caused by the fluctuation of the electrons within the molecules or atoms. Since all atoms and molecules have electrons, so all molecules will have dispersion forces. Dispersion forces are caused by the random fluctuation of the electron distribution of the atoms or molecules. For example, in helium, the 2 electrons are constantly moving, but at a certain point of time, you have 2 electrons sitting on one side of the atom because electrons are negatively charged. So on this side, the electrons are partially negative charged, we use delta negative to represent it. On the other side, which lacks negative charged electrons, the other side is partially positive charged. We use delta plus to represent it. So this type of uneven distribution caused by the movement or fluctuation of electrons is called instantaneous dipole. The instantaneous dipole looks like this for the helium. You have two electrons sitting on one side, and the other side is lacking electrons, so it's partially positive charge. When a helium atom is coming close to the instantaneous dipole, the two electrons will be attracted to this partial positive charge. So these two electrons will be attracted to the partial positive charge. And because this partial charge distribution is caused by the initial instantaneous dipole, so this dipole is so-called induced dipole because it is caused by the original instantaneous dipole. So dispersion forces in nature are the interactions between the instantaneous dipole and the induced dipole. Please note that dipoles responsible for the dispersion force are transient, constantly appearing and disappearing in response to fluctuations in the electron clouds. So for this reason, generally speaking, for a small molecule, the dispersion force is very small. So as you can see, the instantaneous dipole and the induced dipole will interact with each other in between the helium molecules. And these interactions are weak interactions. The attraction force is quite weak. Let's look at some examples. When you look at all the noble gases, helium, neon, argon, krypton, and xenon, we noticed the molar mass increased from top to bottom, and the boiling point also increased from top to bottom. The reason is because the magnitude of dispersion force depends on the size of the electron cloud, which can be indicated by the corresponding molar mass. The larger the size of the molecule, the larger the dispersion force, therefore the higher boiling point. As we just learned, dispersion force exists in all molecules, but the dipole-dipole force only exists in polar molecules. But do remember, since all molecules will have dispersion force already, so polar molecules would have both dipole-dipole force and dispersion force coexisting. Let's look at one example. For example, in formaldehyde, the CO double bond, this is a polar bond. Do remember, all CH bonds are nonpolar. All CH bonds are nonpolar because the electronegativities of carbon and hydrogen are very close to each other. So the partial positive charge on this carbon and the partial negative charge on this oxygen will interact between molecules as demonstrated in this model. The dipole-dipole interaction is much stronger than that of the dispersion force. As you can see, when we compare the boiling point and melting point of these two similar sized molecules, both formaldehyde and ethane have about the same molar mass, which means for dispersion force, both molecules will have about the same strength. However, because formaldehyde is a polar molecule in addition to the dispersion force. Formaldehyde will have a dipole-dipole interaction. This causes the boiling point to be significantly greater than that of ethane. It's about 60 degrees higher than that of ethane. Similarly, the melting point is also much higher than that of ethane. This is caused by the dipole-dipole force in formaldehyde, which does not exist for ethane. So please note, the stronger the total intermolecular force, the higher the boiling point and the melting point. The total intermolecular force include dispersion, dipole-dipole, and hydrogen bonding, and we will talk about hydrogen bonding later on. Before we do that, let's look at how intermolecular force will affect the miscibility or the liquid's ability to mix with another liquid. So in general, polar molecules are miscible with other polar liquids and are not miscible with nonpolar liquids. For example, water is a polar molecule, so it's not miscible with pentane, a nonpolar liquid. So when you look at pentane, you don't need to know the details about the structure, which you should know, but if you don't know, it's okay, because this contains carbon and hydrogen only. These are so-called hydrocarbons. Because hydrogen and the carbon have very similar electronegativity. For this reason, all hydrocarbons are nonpolar. So water and the pentane will not mix. Consequently, the oily hand and the oily stains on clothing cannot be washed away with plain water. Rather, we're going to use soap, which can trap the nonpolar dirt in the middle, and the whole thing will form a micelle type of structure that's dissolving water in that way. What about hydrogen bonding? Hydrogen bonding actually is a special case of dipole-dipole force. But because the strength of a hydrogen bond is much bigger than that of a dipole-dipole, a regular dipole-dipole, so we single it out and give it a new name, hydrogen bond or hydrogen bonding. So what happened is, if the polar molecule contains HF bond, HO bond, or HM bond, they can form a especially strong type of force that is called hydrogen bonding. So basically what happens is the partial charge separation between HF bond is very large because the difference between the electronegativity of hydrogen and the fluorine is very large, causing the separation of the charges be much bigger than the regular bonds. So for this reason, the interaction between the molecules, which is so-called hydrogen bonding, is very strong compared to dispersion and the dipole-dipole force. Because of the strength of hydrogen bonding, it can affect the boiling point and the melting point in a similar way. Let's compare the ethane and methanol boiling points. Methanol, which has a structure as a CH3OH, the detailed structure is like this. CH3 is a carbon connected with 3 hydrogens. So when you look at that, we do have OH bond over here, which is highly polarized because O and H have very different electronegativity, causing OH bond to be highly polarized, or the hydrogen is highly partial positive charged and oxygen highly partial negative charged. So for this reason, hydrogen bonding does exist in methanol, causing the boiling point to be much higher than that of the ethane, which only has dispersion force. Let's look at the hydrogen bonding in water. In the water molecules, if you write the structure for water, water has two lone pairs. Okay, when this forms hydrogen bonding, one water molecule can form two hydrogen bonding. Remember the OH bond. The OH bond is not hydrogen bonding. That's a covalent bond. A hydrogen bonding is not a chemical bond. It is a type of intermolecular force. So the hydrogen bonding you see in the structure is not the OH bond. It's rather indicated by this red dots over here. That's the interaction between molecules. Okay, so oxygen is partially negative charged, and hydrogen is partially positive charged, and they interact with each other. And this interaction is called hydrogen bonding. The boiling point of water is remarkably high for a molecule that is very, very small in size, with a molar mass of about 18. But the boiling point is 100 degrees C. That's really high. This is because of the formation of hydrogen bonding between the water molecules. We have one last type of intermolecular force, which is called ion-dipole force. This exists between an ion and the dipole. So ion is totally separated charge. So this ions is going to exist in ionic compound. And dipole is going to exist in a polar molecule. So for example, when NaCl is dissolved in water, it forms aqueous solution. So in this molecule, you will see chloride, which is negative charged, being surrounded by water molecule in such a fashion that the positive charge at the end of water is directed toward the center. And the opposite is true for the water molecules surrounding sodium ion. Sodium ion is positive charge. For this reason, the partially negatively charged end of water or oxygen is directed to the center. Let's summarize everything. So we have just learned 4 different types of intermolecular force. First, dispersion force, or London force, or sometimes it's called London dispersion force. The strength is relatively weak, but it will increase with increase in molar mass. It will be in all molecules. For dipole-dipole force, it's generated by the permanent dipole, so it only exists in polar molecules. But do remember, polar molecules will also have dispersion force. So hydrogen bonding is relatively strong. It will exist in molecules containing hydrogen bonded directly to fluorine, oxygen, or nitrogen. Or in other words, if a molecule contains HF bond, HO bond, or HM bond, you will see the existence of hydrogen bond. To remember, if a molecule contains hydrogen bond, it will also have dispersion and the dipole-dipole force. For ion-dipole is very strong. It exists in the mixture of ionic compound and the polar compound. For example, when NaCl, which is ionic compound, is dissolved in the polar molecule like water, then you will expect to see ion-dipole force. But do remember, if any molecule contains ion-dipole, it must also contain dispersion force, dipole-dipole, and hydrogen bonding. It will have all 4 intermolecular forces, as you can see in these pictures. Let's work on a few practice exams. Which type of intermolecular force is the strongest? So generally speaking, the intermolecular force that is strongest is ion-dipole, but it's not listed here. So generally speaking, here's the strength of different intermolecular force. It's the dispersion force. It will be smaller than dipole-dipole force, which is in turn smaller than a hydrogen bonding. Hydrogen bonding is weaker than ion dipole. So for this reason, the correct answer is hydrogen bonding. Three molecules A, B, C have nearly identical molar mass. So when you read identical molar mass, this means dispersion forces for A, B, and C are about the same. Substance A is nonpolar. Nonpolar, so for nonpolar molecules, it only has dispersion force. Okay. For molecule B, B is polar. So what force will exist in molecule B, in between molecule B? So polar molecules will always also have dispersion force, which exists in all molecules. But since it's polar, you will have permanent dipole, which will generate the dipole-dipole force. Right? Substance C undergoes hydrogen bonding. So if you have hydrogen bonding, you will have all three intermolecular force, which is dispersion force, dipole-dipole, and hydrogen bonding. Okay. So for this reason, what is most likely to be the relative order of their boiling points? Okay. So remember, the stronger the total intermolecular force, the higher the boiling point. So we expect the C to have the highest boiling point, B in the middle, and A is going to be the lowest boiling point. So answer A is expected to be the most likely situation. Which of the following has the highest boiling point? Highest boiling point corresponding to the strongest intermolecular forces. And do remember, intermolecular force increases from dispersion to dipole-dipole to hydrogen bonding to ion dipole. So when you look at A is nonpolar molecule because it only contains hydrogens and carbons. This is called hydrocarbon. We know this molecule is nonpolar. So if it's nonpolar, that means this molecule only has dispersion force. The second molecule apparently has NH bond. So this molecule is a polar molecule. Not only is polar, it also contains NH bond. So it contains NH bond. That means it has hydrogen bonding as well. Okay. So if you have a hydrogen bonding, you actually have all three. You have dispersion force, you have a dipole-dipole, you also have hydrogen bonding. The third molecule, when you look at this molecule, oxygen is connected to two carbons, which is flanked by three hydrogens. So this molecule is a polar molecule. This is a polar molecule, so it will have dispersion force and dipole-dipole force. For D, it's a nonpolar molecule, so it's dispersion only. E, it has OH group. This molecule is polar. And it also has OH group, which means this will have dispersion, dipole-dipole, and hydrogen bonding. So apparently only B and E have exhibited hydrogen bonding as the strongest or dominant intermolecular force. So the answer would be either B or E. But which one is correct? When you look at the molar mass between B and E, it's about the same. However, because OH bond, is more polar than NH bond. So for this reason, the hydrogen bonding in E is stronger than that in B. So for this reason, E is going to have the stronger IMFs. So E is expected to have the highest boiling point. Next question. Which of the following is least soluble in water? So remember, the solubility or miscibility of two different liquids is determined by the polarity. Polar molecules is more likely to dissolve in polar solvents, and the nonpolar molecules is more likely to dissolve in nonpolar solvents. So water is polar. The least soluble molecule will be nonpolar. Because A is a nonpolar molecule. Why is A nonpolar? Because A, as we analyzed before, A only contains hydrogens and carbons. All hydrocarbons are nonpolar. Arrange the following in order of increase in melting point. Okay. For the melting point, the first thing in the list we should realize, NaCl will have ionic bond that is responsible for the melting. Okay. Ionic bond being a chemical bond, it's much stronger than any of the intermolecular force. So for this reason, NaCl would be expected to have the highest melting point. So this could be the correct answer. A, B, C will be wrong because NaCl is an ionic compound, which means ionic bond is responsible for the melting point. So either D or E is correct. But let's look at this more carefully. All right. So when you look at argon, argon is a nonpolar atom. CO2 is nonpolar. H2O is a polar molecule with hydrogen bonding in between. So that means H2O is expected to have higher melting point than the other two, like CO2 and argon, because both argon and CO2, carbon dioxide, are nonpolar, so they only have dispersion force. So D is the correct answer. And between argon and the carbon dioxide, argon has a smaller molar mass because the molar mass for argon is about 40. Okay, and for CO2, the molar mass is about 44. So for this reason, argon is expected to have a lower melting point than that of CO2. So that's why you see the exact order listed in D as the correct answer. So one more time, ionic bond is much stronger than any of the intermolecular force. Actually, the strongest intermolecular force, like ion-dipole, only account for about 10% of the strength of an average ionic bond or covalent bond. And the hydrogen bond, being very strong, however, it only accounts for about 5% of an average ionic bond or covalent bond. So for this reason, a chemical bond is much stronger than any intermolecular force. Intermolecular forces are playing a very important role in our health. For example, a DNA molecule is composed of thousands of repeating units that is called nucleotides. And each nucleotide contains a base, adenine, abbreviated as A, thymine, T, cytosine, C, and guanine, which is G. The order of these bases along DNA encodes the instruction that specify how proteins are made in each cell of the body. And then most importantly, each strand is held to the other by the hydrogen bond that occur between the bases on each strand. So as you can see in this picture, thymine is perfectly matched up with adenine with the hydrogen bonding in between. And cytosine and guanine is also perfectly matched up with the hydrogen bonding in between. Hydrogen bond plays a really important role in the formation or matching up of the DNA strands. So hopefully now you have a much better understanding of intermolecular force. We'll see you next time. Have a good day.